Hello everyone, my name is Brian Tang. Together with Dakota Sullivan, we'll be presenting our work titled CONFIDANT, a privacy controller for social robots. This is joint work with Bengisu Cagiltay, Varun Chandrasekaran, Kassem Fawaz, and Bilge Mutlu. Robots are becoming increasingly prevalent in sensitive environments, including homes, healthcare settings, and workplaces. Additionally, robots possess the ability to autonomously move throughout these environments and collect significant amounts of data. This combination presents a unique set of privacy challenges that are different from other social agents such as virtual assistants or chatbots. To address this issue, we propose a privacy controller to appropriately moderate information disclosures. Some prior work in robotics outlined the various factors around social boundaries and trade-offs between privacy and personalization. Other work explored tagging recordings with speakers and having the robot prompt users before information disclosures. Our work focuses on automating the decision process for information disclosures. Social robots, which are not programmed to understand privacy boundaries, can cause several issues. For example, the robot could leak some sensitive information or a secret to one of its users. This could be a violation of social boundaries, which could result in a decrease in trust for this particular robot. Ultimately, public perceptions of social robotics could be negatively impacted. So, how can robots protect their users' privacy during interactions? The robot can choose to share only non-sensitive information and keep sensitive details private. In this example, the social robot is deployed in a healthcare setting to facilitate sensitive health disclosures. It must also converse with the patient and cheer them up. When a visitor comes into the room, the robot should keep sensitive health information to itself. However, it could use mundane information from previous interactions to aid in its social capabilities. We will discuss how to achieve this by detailing the design of CONFIDANT, the dataset used to train CONFIDANT, and an initial evaluation of CONFIDANT's effectiveness. How is a robot supposed to distinguish between sensitive conversations and shareable conversations? The first step is to accurately construct the contextual information around the conversation using setting, participants, and norms. The second step is to assemble the contextual information using categories and rules. Here, the topic, sender, and recipient are all important factors to consider. Finally, CONFIDANT filters decisions around information disclosures by creating privacy boundaries from the rules derived in steps 1 and 2. Our design of CONFIDANT assumes a robot is able to process audio information. This includes things like the speaker identity and speaker diarization. After transcribing this audio into text, we extract the level of detail, topic, and sentiment for a given conversation. Finally, we extract several pieces of metadata like location, the number of people, and the types of relationships. The identity, topic, sentiment, and transcription are all provided using machine learning models, whereas the location and relationships are currently explicitly provided as priors. In our design, we use machine learning to construct several pieces of contextual information. These include speaker identity, derived using SpeechBrain and tested on the VoxCeleb dataset, conversation topic, predicted using Google Natural Language and tested on the Yahoo Answers dataset, sentiment, also inferred using Google Natural Language and tested on the IMDb Reviews dataset, speech transcription, using Google Speech-to-Text and tested on the LibreSpeech dataset, and finally, semantic textual similarity using SentenceBERT and the STS benchmark dataset. Finally, we classify the metadata of each conversation into labels for the following categories. We use rule association learning, specifically the a priori algorithm, to automatically map label combinations onto a control level, indicating the sensitivity level of each conversation. So as you can see here, different combinations of labels become rules, and these rules are associated then with low, moderate, and high control levels.
With the framework of CONFIDANT completed, we next needed to collect a dataset to train the elements of CONFIDANT's machine learning models. To collect this data, we developed a series of privacy scenarios for evaluation in a user study. To begin, we developed 16 privacy scenarios based on 7 privacy violation types distilled from communication privacy management theory. These scenarios were also developed following a partial factorial design that controlled for environment, in-home versus out-of-home, the number of individuals involved in the discussion, one-on-one versus multi-party, information sharing behavior, withholding versus disclosing, and appropriateness of disclosure, appropriate versus inappropriate. Along with our 16 privacy scenarios, we developed another 42 control scenarios, which were adapted from movie scripts. All scenarios were written in the form of conversation scripts composed of an initial information disclosure of one's own personal information, followed by a subsequent disclosure or withholding of the same information by the initial recipient to a third individual. An example of one of our privacy scenarios can be seen here. Participants are provided with a picture and written description of the scene's environment, the individuals involved, and the scene's underlying context. In this example, a doctor navigates patient confidentiality while on the elevator with a patient's family member. This privacy scenario showcases a common privacy dilemma in healthcare settings, which is ultimately dictated by the rules and responsibilities of the healthcare staff. Finally, we conducted a user study through Amazon's Mechanical Turk using our curated scripts. Each participant was provided 5 scripts, followed by a series of statements with Likert scale responses based on level of agreement. All statements pertain to privacy, trust, and appropriateness of the scene and its characters. In total, we collected data from 174 participants. Here we can see examples of the statements participants responded to. Participant responses were then used to train Confidant's machine learning model to calculate privacy scores. These scores ultimately dictate the level of restriction a piece of information should be held to within a given context. If information is classified as low, the information can be freely shared. Moderate information can be shared to a low level of detail. Highly restricted information cannot be shared at all. With our privacy controller trained, we began developing an additional user study to evaluate Confidant's effectiveness. To do this, we adapted a test set of 12 scenarios for ease of filming. Next, we implemented Confidant on a Misty 2 robot platform, which would eventually be the robot present in our videos. Finally, we filmed each scenario. All scenarios involved a 2-person conversation with Misty present, followed by a conversation between Misty and a third individual. Next, we ran a second MTurk survey asking 95 participants to watch video scenarios of both a baseline robot and one with the controller implemented. Each participant responded to statements corresponding to the following key evaluation factors: privacy, trust, and social norms. We asked participants to evaluate the privacy awareness of the robot by ranking statements like, "The robot kept sensitive information private." We also asked participants to evaluate the trustworthiness of the robot by ranking their comfort level if they were to converse with the robot. Finally, we asked participants to evaluate the social awareness of the robot by ranking whether the amount of information it disclosed was appropriate. Overall, participants perceived the robot with the privacy controller filtering its responses as more privacy-aware, trustworthy, and socially aware compared to not having a controller. This can be seen in each of the pairs of density plots on the right. These results indicate that having conversational filters that model privacy boundaries can improve user trust and adoption. It is worth noting that the robot can still make mistakes or disclose too much information. We envision that our controller Confidant can be deployed in existing robots, learn new rules, and adjust to its owners over time. During our first MTurk survey, we also collected a set of privacy indicating phrases such as, "Can you not mention this to anybody else?" These phrases can be used as user input to create explicit rules and prevent future mistakes. Here the user asks the robot to keep something secret. The robot then processes the audio and transcribes it into text, finally performing semantic textual similarity to detect these key phrases. In conclusion, we've discussed that privacy is a core concern of social robots, and using a controller to filter a robot's speech using context from conversations is one solution to this issue. The inclusion of privacy controls in social robots can improve trust and accelerate adoption by users. For more information on our project, please check out our paper, dataset, or GitHub. You can see more projects on our websites, or feel free to contact us at one of the emails listed here. Thanks everyone for listening.